So in this presentation, I'll be focusing on the role of the new codecs and how we can use machine learning to improve those new codecs in video processing and delivery. So for the past few years, we have roughly every 10 years, we have a new generation of video codecs, which aims to deliver to double the compression efficiency over its predecessor. So the big problem is that that increase in efficiency doesn't purely come from switching to a completely different paradigm, but mainly from refining existing tools and also increasing the number of those tools and exploring more options. For example, we started on MPEG-2 with no interprediction. H.264 pushed that to 9 interprediction modes. And HEVC raised that number to 35. So you can see adding more modes will obviously, will improve efficiency, but will also impact the computational requirements of the codec. The same was true for block sizes. MPEG-2 H.264 used a fixed block 16 by 16 pixels blocks, while HEVC extended to a new concept of CTU, where you can have blocks as big as 64 by 64 pixels that then can be split down to blocks as small as 8 by 8. So you have almost 4 layers of different sizes of blocks hierarchically that you have, you potentially can use. So you may need to try them all to decide which one is the more efficient for the application. Also, you have more flexible GOPs, more flexible referencing, everything contributing for efficiency, and also more sophisticated motion estimation, for example, going as low as a quarter pixel, and now with H.266 VVC, we are defined motion estimation, where instead of predicting a single motion vector for a block, you can predict 3 motion vectors or 4 motion vectors in the case for each corner of the block, and then perform a geometric transform that is far more accurate, but of course has computational costs. So as you can see, aside of the increase on compression efficiency, we are seeing an increase on computational complexity. And most of you can think, well, that's probably not really a problem because computers are getting better. But even if you think about, Moore's law states that every 2 years, computational processing doubles in power for a given cost, which may be a bit optimistic currently, and then you think on 10 years you'll have 30-fold increase on efficiency. But if you look at VVC, it's around 16 times more complex than HEVC, or 10 times maybe if you use SMD instructions, which you think, well, it's still kind of bounded in the Moore limit, but apart, on par with all of this, you have increases in resolution, since MPEG-2 targeted mainly SD, H.264 targeted HD, HEVC 4K, and now we are thinking on 8K and beyond. So you can see how all of this is pushing the costs of the systems and the complexity. To deal with this, codecs usually introduce a concept of presets, which is, depending on how much computation you have available, you can disable certain tools in the codec to make it more lightweight. That will impact your video quality, but it will cost you less computationally, and that may be required to achieve real time, for example, or to be able to run more channels in your system to reduce the price point and costs. That's the approach taken, for example, by X.264 and X.265, which are open source implementations of both HEVC and H.264 codecs. And here I have a simple example where you can see the presets range from ultra-fast, which is very lightweight, that on this particular platform you can achieve 30 frames per second, but you can see the final file size for a given quality is much larger than more exhaustive presets that use more tools. So this plot also shows you 2 things. One, you have diminishing returns. You start having to spend a lot of computation for having small gains in quality after some point. And the second, that you look, for example, to this faster profile, it actually costs less computationally than some of the more complex profiles, but still delivers a better compression. And why is that? Because those presets were optimized for a wide range of content. And what's true for sports may not be true for news or for cartoons. So the profiles can be quite suboptimal in the point of view that you will dimension your system to achieve a density in a preset, but then the reality of your content and your application can be very different, and you may be, either not achieving the full potential quality of your system or just waste resources. So, again, you know, and this is also true for, this is not only true for the ITU family of encoders, but also for VP9 and AV1. You usually end up having to trade CPU cost for bitrate efficiency. And that will have the direct impact in your application cost. You can go to a system with very high video quality, but that will require lots of processing power that will be probably too expensive to deliver, or you may struggle to achieve real time for a particular application. Or you may just be willing to compromise on quality to deliver your content more cheaply, basically. So on all of that, you can still have better algorithms that allow you to deliver a quality or better quality without impacting the CPU needs that much. Or you can improve your CPU management so that you achieve the best possible compression efficiency on the resources you have. And that's where we propose to use AI. We all think about AI, about those brand new disruptive technologies like self-driving cars and voice recognition and everything. But in fact, you can use it to optimize other simpler tasks on existing problems. And in this case, the idea was, well, what if we could use AI to better tune our encoders and better manage our CPU usage so that we can deliver a better encoding for the same, for the same resources and for the same codec. So our first target was to manage the high-level encode strategy. So basically, if you look, every content will have its own specificity. So if you look, for example, at this cartoon, you see that there is quite a bit of spatial detail because there's lots of textures, sharp edges, and everything. But motion is quite simple and easy to track. There's also not a lot of transitions, you know, it's just like soft flowing content. Well, if you go to something more like sports, you probably are far more pressed on transitions because you'll have different cameras, different angles, fast pans and everything. But probably the motion precision is not as important because you'll suffer from camera blur, other artifacts, masking and everything. On the other hand, spatial allocation is probably not as important as well because there's masking when everything moves very quickly in the picture. You cannot fix on particular issues, while in a slow-moving content, those become much more obvious. If you look, again, to different content like news, on this case, you barely have any transitions. You have very little motion, but you are very aware of the spatial allocation. Everything that degrades the edges in the text and everything will become very apparent and very annoying for the viewer. So the idea was, okay, instead of using those out-of-the-box presets where everything, you know, all the parameters have been turned for a wide variety of content, can we actually use AI to classify different types of video and try to understand which tools in the codec can benefit the most our video quality? By doing that, we can then selectively turn on and off tools instead of switching to a completely different preset that was optimized for a generic content. So how did we do that? Well, first, we went through a big training process. So you start with a very big library of content that you try to encode, you change the parameters, and then you try to understand how the characteristics of the input video were affected by turning on and off some of those tools. By using machine learning, you can just, well, develop models far more complex because, you know, it will be very time-consuming for a human to change each one of the presets and then see what the impact was and then plot all the data and try to get a model somehow fits everything. So you can just automate the process, try the different parameters, do an input video analysis, see if the metrics you have in your input analysis correlate with your parameters, and train just a neural network that can correlate both. After you do that very costful process, you can just get that neural network and implant it in your codec. So it should be much more lightweight. And then on real time, you can just, for example, use a look-ahead encoder, which is a very lightweight encoder that runs before the main encoder to help on tasks such as rate control and sync-cut detection and that kind of things. And you can use all the information from that look-ahead encoder, parse it to your neural network that then do the inference and try to to give a classification to your content. That then your encoder can use to, in a frame-by-frame basis, tweaks its own parameters so that you can optimize your compression efficiency for that content. So what does that impact? By switching different encoders, you're in fact changing your resource allocation to perform different tasks. And again, for example, in this case, you may not want to spend a lot of resources on motion estimation because the motion is quite simple. So why try to look in big search ranges, lots of references, when in fact, you know, a simple approach gives you already good enough results. In the other cases, in the news, for example, you go a bit the other way around. So you should probably put far more resources on looking at the spatial allocation, and again, not spend a lot on motion estimation. While in sports, you can save some of the processing of trying so many block sizes and estimation modes to achieve a good spatial allocation and spend those resources and not try to explore the complex motion that's going on. So what are the first benefits, or the big benefits? Well, first, if you use the canned out-of-the-box presets, you need to dimension your system for your worst-case scenario. So in this case, if you had given like your hardware resource, you check what the density you want to achieve, and you see which one is the best preset that can run on those resources. But for some content, that will deliver you, pardon me, very good quality, while some other content that may not perform as well. So by using a frame-by-frame switching, you can basically spend less resources on easy content and use those resources on the harder content. So that guarantees you you're still in your density without having to dimension for the worst case scenario. So this also maximizes your infrastructure usage, because for example, in this case, imagine that you try one preset and you can only fit 2 channels in your hardware resource. So you think, okay, maybe I can go to the next better quality preset, but you realize that, oh, I won't be able to fit 2 channels, so I have to settle with the lower preset. That means that a big chunk of your hardware will actually be unused, and because you've been dimensioning for the worst case scenario, this can actually be quite significant. By using an adaptive approach, you can just, you have the resources available, and by using a feedback loop, you can switch on more tools so that your encoder can use the full hardware resources. And then you know that if your source changes considerably, your algorithm can then your encoder can start disabling or restricting some of the tools so that you can still guarantee you fit inside your hardware resources. So those are some of the results we achieved. So by doing this, for a simple example, where we would compare a fixed preset mode for a given hardware platform, we've seen that, for example, we could fit 2 channels, 3 channels at this preset wouldn't guarantee real time. So it was, in this example, we use a 1080p top resolution ABR source. And for a fixed hardware resources. We could see that the quality increased quite significantly because you're actually using all your hardware resources instead of a restricted part of it. On average, for many application cases and different combinations, we got around 19% gain, or in the case you can have this, an increase in 19% on the SSIM with the same resources, or in extreme cases can be all the way up to 40%, where the percentage of unused resources is larger. So after this high-level strategy of adapting parameters, we try to go a step further, which is, can we actually fine-tune all the small aspects of the encoder, but not the main configuration parameters, to achieve a better video quality? So that was the next step. And our first attempt was at HEVC coding tree units. As I mentioned before, instead of 16 by 16 macro blocks, HEVC used CTUs that range from 64 by 64 pixels and then splits it in 32 by 32, 16 by 16, and hierarchically to 8 by 8. Usually, bigger CTUs are used on a video that is easier to encode, because usually using big blocks costs less bitrate, but results in a slightly, or in most cases, a lower video quality, because you're not able to track the detail as efficiently, while areas with more detail usually require smaller partitions. But the traditional approach is use the entire tool set is to try all this combination of block sizes, like in a quad tree, and then choose the best option. And this is very time-consuming or CPU consuming. It's an area where you can save lots of computation if you would be able to predict how those particular blocks will be split. And you could just avoid doing some options that probably you're not going to use. So by starting, by looking into it, you can see that, as I mentioned, usually you tend to use smaller blocks on areas that are more detailed in order to be able to track fine detail and sharp edges, because you'll be using smaller transforms as well that can better represent higher frequencies after quantization. But there's also, obviously, the dependence on the bit rate. If you have a low bit rate, you are more concerned about saving bits than with the quality. So you may choose to segment as little blocks as possible, because segmenting blocks will generate extra syntax elements that will consume your bit rate. But while at higher bit rate, you're more concerned with the quality and not necessarily with the bit rate. You have more bit rate to spend, so you end up splitting more where you can achieve benefits with that approach. But that's not the entire story. You can also see that because there are temporal predictions. You can see that some areas, for example, in the players, they can be high detail, they can be moving, but that element was also in the previous frame. So you can predict it very well and still encode it with a big block. So predicting where we're going to use each size of block is not straightforward to come with the same heuristic or approach or model. So in this case, we again used an offline training process. So we basically encode a big data set of video content using different, using a full search where all the modes are tried. And then we just train a neural network that try to replicate the splitting decisions based on input metrics such as gradients, texture, the intra and interprediction residues, and also frame types and the KP that is directly influenced with the bit rate. So we could train that neural network offline in a very big set of content. Then again, get the trained neural network, put it inside the encoder, and perform a real-time inference. Again, in this case, everything is about a compromise. You can go through a very complex neural network that is very good to infer your splitting, but costs a lot of the resources. So what's the point of trying to save on calculating all the modes than if you spend more than that to try to achieve that inference? Or you can go to a smaller model, which is still good enough, and performs adequately, let's say. So we tried different models until we achieved something that we were happy with. And also, because if you think about it, when you try to decide to infer how the block will be split based on the input metrics, what your neural network returns you is a probability. It's like, well, I think that this block will be split with 89% of confidence. So you can actually use a half-term, a dual decision thresholds to trade some of your computational savings to a more accurate classification. Because, for example, you can go for a binary approach. You get your return probability, and if your neural network thinks your block should be segmented, you segment it and you don't even try the non-segmentation option. Or you can go to another, well, more subtle or more, well, cautious approach where you actually, well, if your network is really confident your block won't be split, you will only try the non-split option. If the network is very confident you should split it, you will split it and not try the non-split option. But for intermediate probabilities, you can still try both. That means that you save less, but you are not potentially losing performance because you're still doing some full search for the cases you're not sure. So here I have the results of for a particular example with a 4K sequence running real time at 60 frames per second, so quite a demanding scenario. And in this particular case, the reference preset will, for example, have to disable the 64 by 64 blocks because they were too costly. And otherwise, you wouldn't be able to achieve real time in that platform. Could probably go for a more higher performance platform, but that will have cost implications. By using the neural network to infer inside the encoder and not testing some blocks, you can see that we were able, in this particular case, we were able to enable the 64 by 64 blocks that usually are very useful on plain areas. So by doing that, we were able to improve the quality on around 10%. By also reducing the computational cost. And you can see that, well, 100% is just the normalized cost of the fixed preset. So you can see that at a lower bit rate, you save more because you're more concerned about the bit rate. You're not as concerned about the quality. So you can discard more modes. By discarding more modes, you save more bit rate, more processing. While at higher bit rates, you usually have to try still more modes because your network will still be slightly uncertain and you may compromise too much to go to a binary approach. So in this case, again, you're using less resources, but then you could, for example, by linking it at a previous dynamic switching of other parameters, you could, for example, in this case, reuse the computation you saved to actually enable some other tools that will push you the quality even higher. So you can see that you can actually combine those two techniques, because one is tweaking the parameters while the one is fine-tuning specific tools in your codec. We've seen the biggest gains where the alternative is very CPU intensive. So you've seen that on the case you have all the block sizes and you have to try them all. You can save quite a lot by using this inference and testing less of them. And you also achieve better gains the more complex your content is. Because, for example, if you are encoding something that is easy, like the news or a movie with not a lot of action, even a not so tweaked algorithm that doesn't use all the tools will perform really well. But if you go to extreme cases like sports, you need to have much more tools enabled to be able to achieve the same quality. So by combining both, you can just make a much more efficient use of your CPU to boost your bit rate or your quality, or to lower your bit rate for a given quality as much as you can. So in this example, we've been really looking at cases where we didn't use AI to completely change the paradigm, but just to adapt some existing codecs and some existing technologies. And on those codecs, there's still many other areas that can benefit from this kind of approach. For example, you can estimate the likelihood of inter and intra predictions to, again, shortcut and not compute all with minimum penalties and video quality. You can also shortlist directions on interpredictions, or also try to estimate skips. So again, you can compute less modes without impacting the quality as much. And then there's also, we've been exploring those other areas where AI is actually giving you a full new load of applications that can help you monetize your content and create new applications. One of them is super resolution. So in this case, we've been using generative adversarial networks to create super resolution upscales of, for example, HD video. So for those of you that are not familiar, it's instead of using a simple filter to upscale from HD to UHD, you can use some machine learning that cleverly learns how the downscale affects the image to then try to revert it to create high quality UHD versions of your 4K content. And we are also actively looking at content semantic analysis. So as Sander was focusing on targeted advertisement, you can just use, or we've been using AI just to try to classify content and to try to understand what's going on in the picture and the scene, and use that as a further level of refinement for your target advertisement. For example, you can look at if it's a cookery show, for example, you can detect, oh, this is a cooking program, so let me go to advertisements of cooking utensils or pots or foods. So you may think, okay, maybe your content or engine already has some context, but sometimes, this involves quite a lot of human input, and by doing it using machine learning, you can detect far more types of content and do it in a cheaper and more agile way. And this can also be, used to go down to every little detail. For example, determine automatic captions, or even audio description. So to provide a description of the scene to, for example, video impaired people, or generate automatic subtitles based in the audio. So everything reduces human input, can reduce costs. So you can see that on top of all the refinements on existing technology that you can achieve with machine learning, it also opens that whole new world of options and applications that you can use, well, that can be monetized by video operators. Thank you.